All right, let's see if we can solve example 5 here, which is a variation of example 5 in section 5.2 of your book. And this is another system of equations, 2 by 2, two equations and two unknowns, and they look fairly straightforward. However, I think when we solve this, we'll find that it's in another special case. So let's do the 5 steps. Step number 1, solve one of the equations for one of the variables. If possible, solve for a variable that has a coefficient of 1 or minus 1. Ooh, this is already done here. So that's easy. We just copy that. X equals 12 minus 2y. And 1 is done. That's pretty easy. Number 2. Step number 2. Substitute the expression found in step number 1 into the other equation. Well, this was equation 1, so the other equation must be equation 2, which is 2. All right, we're going to substitute for x, so let's make some room here. Plus 4y equals 24. All right, so we're going to substitute this into there. We get 12 minus 2y. The equation you obtain should contain only one variable. Well, I only see one variable, and that's a y. So step 2 is done. Step 3. Step 3, solve the equation you obtained in step 2. All right, let's take a shot at it. Break down the parentheses by distributing the 2. 2 times 12 is 24. 2 times minus 2 is minus 4y. Plus 4y equals 24. All right, we can solve this. We've got 24. Well, that's not going to have much going to happen there. We have two like variables, interestingly though, but when we add them together we get 0. The right-hand side of the equation is 24. We get this interesting situation where we have 24 equals 24. No matter what y is, we get 24 equals 24. Well, this is true. All right. This is a case where we have what are called dependent equations. What do we mean by dependent equations? Well, to see this, what we're going to do is we're going to take equation number 1 and equation number 2, and we're going to make them into slope-intercept form. Okay, and see and compare them. So equation number 1 is x equals 12 minus 2y. All right, let's flip the sides just to start out with. That's nice and easy to do. The equation's still true, whether the right-hand side is on the right-hand side or the left-hand side is on the left-hand side. Oops, that's 12 minus 2y equals x. All right, let's get rid of the 12. Minus 12 minus 12. That goes away. This becomes minus 2y equals x minus 12. Divide both sides by minus 2. Okay, and what does that get us? Well, that gets us y isolated on the left-hand side, which is just what we wanted to do. And we end up with minus a half x minus 12 over 2. I'm sorry, over minus 2. So this becomes y equals minus a half x. That goes into that once, that goes into that 6 times, and it's plus because these are two minuses. Alright, so that's equation number 1 in slope-intercept form. Let's do equation number 2 in slope-intercept form. So we start with it in its standard form. 2x plus 4y equals 24. Okay, so we wanted to have y on the right-hand side, so we're going to move this over there. by subtracting 2x. We subtract 2x. What happens? We cancel that, and we get plus 4y equals minus 2x plus 24. And that plus sign here is superfluous. Don't need it. Alright, so we're going to divide both sides by 4, so we can isolate y on the right hand, on the left hand side. Forgive me. Here we go. That's 1. 1 times y is y, so we've isolated y. So we have minus 2/4 x plus 24 divided by 4. Alright, y equals minus 2/4. Well, 2 goes into 2 once, 2 goes into 4 twice. So that's minus a half x. Plus, 4 goes into 4 once, 4 goes into 24 6 times. And that's 6. Oh my goodness, this is equation 2. You'll note, equation 1 and equation 2 are in fact the same equation. They just look different. So that's the notion of dependent equations. We can say, in a sense, that the way we got equation number 2, all right, is by multiplying it times 2 times equation number 1. So we can say that equation number 2 is dependent on equation number 1. Now, since these are the same line, when we plot them, right, we're going to get just one line. All right, and up here, the y-intercept is going to be 6, so that's the point 0.6, and it's going down, and it's going to go down. It's going to look like that, and basically that's it. One line. Since it's one line, every point on that line is a solution. And since there are infinitely many points on that line, there are infinitely many solutions. So this dependent set of equations results in an infinite number of solutions, which is another one of our special cases. Infinite number of solutions. Okay, you know the drill. Time to test yourself, see if you actually know how to do this. This is another system of equations which I think you'll find is the same special case. It's on page 296. Give it a try. Good luck.